Hi everyone. Yeah, so what I wanted to do is run through a number of things that relate to sort of farm level issues, if you like. You can see there. Now, I'm not going to talk very much at all about forestry and offsetting. That's a big topic on its own, and I'm not going to talk about soil carbon, but happy to answer questions later if the need arises. First thing I'll do is just give you a little science lesson. Most ag economists have a bit of a narrow education, so I thought I might broaden things out a bit. So in terms of emissions from our ruminant systems, if you like, pasture absorbs CO2. It's as part of photosynthesis. A lot of it goes back out as respiration. But basically, the animal eats the pasture, and within the rumen, as part of the digestion, there's a significant amount of hydrogen ions produced. Now, if nothing was done with those, the animal would die, but evolution has sorted that out. There's a number of bugs within the rumen that scavenge that hydrogen. Now, the main ones of which are called methanogens, which gives you a little clue. Basically, they scavenge those hydrogen ions, turn it into methane, which the animal then belches out. The pasture also contains protein, obviously, and again, the surplus that isn't required by the animal through digestion, the vast bulk of it goes out the back end, particularly as urea in the urine, and is converted in the soil, and that's where we get our nitrous oxide emissions from. Now, coming back to methane, if you count up all the carbon atoms that are circulating, we're actually carbon neutral. However, we're not greenhouse gas neutral because some of that carbon gets turned into methane, albeit for a short period. And of course, you've still got your nitrous oxide emissions. So that was just a little background, if you like, in terms of what are the key drivers of greenhouse gas emissions at a farm level. And the first, by quite a high degree, is the amount of dry matter eaten. So there's a direct correlation with methane, roughly 21 grams per kilogram of dry matter, and there's a strong correlation with nitrous oxide. Key driver of nitrous oxide is the protein level in the diet. Our pastures generally are very high in protein, which is why we're so good at producing meat and milk, but does cause other problems. And then the third one is the amount of nitrogen fertilizer applied. Why do we apply nitrogen fertilizer? To grow more grass. So you go back to point one. So if you're looking to reduce your greenhouse gas emissions, at the moment, guys, you're looking at the toolbox that's available to farmers, other than forestry and offsetting. So the short story is you have to reduce them all. And that in turn creates some degree of fun. Now, I just wanted to touch on some of the research that's happening at the moment. There's some interesting things happening. On the genetic side, we have developed or identified low methane rams. Hopefully they'll be commercially available in the next 2 to 3 years. LIC and CRV are doing a lot of work identifying low methane bulls, and that's a matter of when, not if. Once I've identified them, they then have to be progeny tested, etc. But I would be optimistic that within about 5 years, we can get low methane animals in the dairy industry. And I would be quite optimistic of a rapid uptake, given that 70 to 80% of our cows are inseminated. Methane vaccine, a lot of work happening on that. New Zealand leads the world in that respect. The good news is they can get it to work in the lab. The bad news is they haven't got it to work in the animals yet. The idea there is that you vaccinate the animal, they'd produce the antigens in the saliva, swallow that down into the rumen, and those antigens would then knock out or at least slow down the methanogens. promising, but yeah, a good decade or more, I suspect, before we're likely to see it. Methane inhibitors, there's a lot of work happening, but both in New Zealand and around the world. In essence, these are the chemicals that you'd feed to the animals that again knock out the methanogens. There's a Dutch company, DSM, that's looking to register an inhibitor in the EU this year. There is work happening on that within New Zealand. The main issue is it's very short-lived. Basically, the animal has to eat it in every mouthful, so that suits a total mixed ration type approach, but not our grazing systems. So the idea is to find either a long-term inhibitor and or a delivery system, such as a capsule or a bolus, that we can get it into the animals. Similarly, with nitrification inhibitors, most of you probably remember DCD from a few years back. Again, we have identified, I think it's about 5 or 6 different nitrification inhibitors that are much more efficacious than DCD. But the idea is, they'll be applied to the pastures to reduce both nitrogen leaching and nitrous oxide emission. Still, I'd say probably at least 5 years away in that respect. We know that some foragers reduce both methane and nitrous oxide, forage rape, fodder beet, for example, plantain for nitrous oxide. The issue with them is that they have to be a significant part of the diet, usually 30% or greater, before they have an effect. So the issue is how you achieve that on a predominantly pasture-based regime. There's other things, no doubt you've heard about the GM ryegrass that ag research has developed. It's a high lipid ryegrass, and the theory, it hasn't been tested, but the theory is because it's high lipid, it would increase the efficiency of digestion and reduce methane. And we've all heard about seaweed. Seaweed certainly works, can work very well indeed. The problem we've got is that the chemicals within seaweed that reduce methane are very nasty chemicals. And there's a huge amount of work to be done to be shown that we can actually use those. And then I'm not sure if you're aware, but there's a company that's developed basically a sort of a mask you can put on the animal. When it burps out the methane, it's sucked into a catalytic converter and converted to CO2 and water. Not sure how practical that is, but just thought I'd mention those because I want to come back to them when we start looking at some of the costs down on the farms. Now, just moving on, this is a couple of case study farms that we've worked on. And what I wanted to do here is really come back to the question of, if you want to reduce your greenhouse gas emissions, the key thing you need to do is reduce the amount of dry matter eaten. So you don't reduce that at an individual level, an individual animal level. You're really looking at reducing stocking rate. So that's fine. So if you look at both those farms there, what we did is we reduced our can numbers by 10%, but made no improvement in productivity. So certainly we got a reduction in greenhouse gas, and we also sort of trashed the profitability somewhat. So if you're reducing your stocking rate, you need to then look at increasing your per animal productivity in order to try and maintain the financial viability of the farm business. And again, if you look at both those farms there, we reduced our cow numbers by 10 and 15%. When I talk about increased productivity, what we did was increase our per cow production within the envelope of feed available on the farm. And certainly with farm 1, we were getting reasonably good greenhouse gas reductions and quite significant improvements in their profitability, which would indicate there is quite scope on that farm to improve efficiency. If you look at farm 2, again, we still got reasonable greenhouse gas reductions, but we well, we reduced the loss in profitability, if you like. And that comes back to an issue in the sense that if you're operating an average farm, yes, you've got scope to improve your efficiency. If you're operating a high efficiency farm, you're slightly between a rock and a hard place. We planted 10% of the farm, each farm, in pine trees. That was just to again look at the impact on greenhouse gas. Again, significant reductions because of the offsetting, but again an adverse impact on farm profitability. If we planted 30-odd% of the farm in pines, we were carbon neutral, but the farm was financially toast. The other little thing of interest while we're on here is with Farm 1, we planted 10% of that farm in gold kiwi fruit because that was certainly an option, which was a $10 million capital expenditure, which we built into the situation. As you can see, that dropped, with horticulture, you average down, if you like. So that dropped our greenhouse gas by 9%, and gold kiwi fruit being gold kiwi fruit, we had a slight improvement in our farm profit. Now, just for your interest, that's the way the farm's gone. They couldn't afford to go to gold, so they've gone to green. They planted 13% of the farm in green. That'll drop their greenhouse gas emissions by 10%, and their EBITDA will improve by a mere 130. Out to right there, just for your information, some of the shadow prices which we calculate. I want to come back to those, but the main thing there is, as you can see, there's quite a range, including some negatives. If they're negative, that would indicate that perhaps the farm should be looking at implementing that strategy regardless. Just moving on to a couple of sheep and beef farm case studies. Just looking at Farm 1 initially, this is a reasonably big farm, 1,500 hectares. They had some forestry on the property, which wasn't in the ETS. And as you can see, the gross emissions were 3.3 tonnes per hectare. If they brought the existing forestry in, that would drop their net to 2.5. We then planted up increasing areas of the farm in pine trees. And as you can see, we planted an extra 140 hectares. Basically, the farm's carbon neutral. And then with increasing areas, we had a surplus of carbon. If you look at the EBITDA figures there, the figures on the left-hand side of the slash is the impact on the farm business without bringing carbon into the equation. The figures on the right-hand side is where we sold the surplus carbon at $25 a tonne, which was the price on the day, which certainly lifts things up significantly. The issue there, if you know anything about forestry in the ETS, is that under the averaging scheme, you only get that for 16 to 17 years, and then you're back to a production forest operation. Both the farms there, again, we went through the process. We dropped our stocking rate by 10% without changing performance. Again, that reduced our greenhouse gas emissions. Again, had a negative impact on our profitability. So we dropped our stocking rate by 10% and looked at improving productivity in the sense of increasing lambing percents and carcass weights and that sort of stuff. Farm 1, again, a good reduction in greenhouse gas and a positive impact on profitability. Farm 2, again, a drop in greenhouse gas, and farm profit was still negative, but at least we'd reduced the impact, if you like. And again, just a reflection of the impact given different intensities of farming. The only one I'd point out, other one I wanted to touch on there rather, was Farm 1. If you, the bottom one there, decrease our ewes by 20%, increase lambing percent. The farm was running about 6,500 ewes, so we said let's cut that down to about 5,000, increasing our lambing percent up to 100, from 127 to 160, and also increase our carcass weights on beef. Again, a good greenhouse gas reduction and an improvement in profitability. I don't want to go too much more into that, but I want to come back to that when we start talking about the difference between modelling and the real world. And there out to the right-hand side again is some of the shadow prices relating to those different scenarios. And again, as you can see, quite a variation. And then just, this is a cropping farm. It's a maize operation in the Waikato. The main thing here is to illustrate in terms of arable cropping, vegetables and horticulture. If you haven't got animals, you haven't got methane. So your only issue, if you like, is nitrous oxide, which is directly related to the amount of nitrogen fertilizer you use. So coming back to this question of on-farm change and looking at farm systems, yes, we can fine-tune our farm systems. As a generalisation, we were getting 2 to 10% reduction, a variable impact on profitability. The key factor really comes back to reducing stocking rate with the idea of achieving a reduction in the dry matter eaten. But as I've mentioned, if you're going to do that, you really need to improve your per annum productivity to maintain your profitability. Which then raises this issue of what's going to happen in the real world. Reducing stocking rate and improving productivity is for many farmers a big step, although I'd have to say, guys, we've got farmers who are doing that already. But it is absolutely reliant on a significant improvement in farm management. So the farmer expertise, if you like, has to take a big step up. Now, if I could go back to that sheep and beef farm where we increased our lambing percent from 127 to 160%, you could ask the question, is that technically feasible? And the answer is yes, it is. But for that farm to achieve it, it would have to go through a range of changes, if you like, and I would say it would take at least 10 years to do that. So it's not an overnight exercise. The other thing is, if you're lambing 160% in hill country, you've moved up the risk continuum, if you like. So you're now operating, yes, you've reduced your greenhouse gas, yes, you're making more money, and yes, you're running a much higher risk operation. So that, again, is something farmers need to take into account. Just to give you some idea of the level of emissions from our farms, getting good data on this is pretty scarce. But this is a 2017 study by Dairy NZ. So the average dairy farmer is putting out 9.6 tonnes of biological greenhouse gas. That's methane and nitrous oxide. The range being between, let's call that 3 to 19, which directly relates to the intensity of the farming operation. On the sheep and beef farms, this is a 2020 ag research study. The average of 3.6 tonnes per hectare per year. That's CO2 equivalents. And the range from 0.16 through to 7. So again, a significant range, and again, that really relates back to the intensity of the farming operation. Just touch on the intensity of emissions, which is kilos of CO2 equivalent per kilo of product. There's a lot of discussion around that, if you like, in the sense that New Zealand, internationally, as been mentioned, we are very efficient. We're at the top of the chain, if you like, particularly around dairying and sheep meat. The issue, if you like, if I take dairying as an example, if I wanted to drive down that emission figure, I would just intensify my farm operation. So that didn't reduce my intensity of emissions, but it would increase my absolute emissions. And it's the absolute emissions that farmers are going to get taxed on. And just to give you some idea, this is using the ETS price. Interestingly, it was at $50 a tonne. Yesterday, it went to 60. I'm not sure if you're aware of that, which is a bit of a puzzle since the government is supposed to put a cap of $50. But I just guess it shows the power of the markets. Anyhow, $50 a tonne and a 5% liability, which is what farmers will face in 2025. The average farm, the average dairy farm, you're looking at about a $3,700 cost. The average sheep and beef farm, almost $6,200 cost. Now, it's interesting when I'm talking to farmers about costing and this, I say, so what are you going to do? A lot of them have said, at that cost, I would simply write a check, which is probably economically a very rational thing to do. All things being equal, the well, for industrial emissions, the free allocation has been reduced. The decision's been made on that. That started last year. So it's reducing it at 1% a year through the 20s, 2% a year through the 30s, 3% a year through the 40s. As I say, agriculture comes into the scheme of things in 2025. I would be reasonably unsurprised if the same increase in liability doesn't hold. And if you go down those tables, those costs mount very quickly. Just talk briefly about the point of obligation. Two options. First is at the processor level. In other words, the processor would pay the tax and pass that on to the farmers with reduced payouts or schedules. The government likes this one because administratively it's much more efficient, but the cost is hidden to farmers, so there's no direct incentive to actually do anything. As an aside, guys, apart from the price rise yesterday, everyone in New Zealand is paying about 12 cents a litre on petrol. I'll be very surprised if anybody actually knows that, and of course it's having no impact. If the price is applied at the on-farm level, the cost is very explicit, and that provides an incentive to change. And that's part of the drive with Hiwaka that Kelly was talking about, is to look at applying any cost at an on-farm level. And then just for your elucidation, if you like, the average Waikato dairy farm, $50 a tonne CO2 equivalent, 5% liability. Processor cost, taking into account both milk solids, meat, and the tax on nitrogen that had come in. The cost of that farm is, let's call that $3,900. If it was applied at the on-farm level and the farmer is producing 11.3 tonnes of CO2 equivalent per hectare, it's costing them about $3,400. So close, but some slight difference. I then just wanted to, looking forward, if you like, and the implications of climate change in New Zealand and the implications for our farming systems. So the 2015 graph there shows what a wonderful temperate country we are. And then the measure, this was modelling by the Royal Society, and they looked at number of days exceeding 25 degrees. 25 degrees is important in the sense, once you get above that, you're starting to induce heat stress in animals, and ryegrass will pack a seed and not grow. Anyhow, if you look at 2100, which is where we're heading, the short story there is the upper North Island is now subtropical. So we won't be growing C3 grasses, we'll be growing C4. We won't be farming Bos taurus animals, we'll be farming Bos indicus. If you look at the east coast of both islands, you won't be growing much without irrigation, which has some implications for the hill country along both those coastlines. You look at Central Otago will be a desert, and you won't be growing anything without irrigation. And it also has implications for horticulture in the upper North Island. Unless we can chemically vernalise kiwi fruit, it won't be growing in the Bay of Plenty.
Just a couple of minutes, Phil, okay.
Yep. So interesting sense in terms of where we're heading and the implications for our farm systems. So it's going to be warmer and wetter in the west, warmer and dry in the east. We're going to see more extreme events, floods and droughts. When I say it's wetter in the west, that's more your winter, spring. Talked about the impact on the North Island. but we are going to be much more reliant on irrigation, both for our pastoral and our horticultural systems. And as a result, I think we're going to see a lot more divergence in our farming systems around the country. We need farm systems that can cope with this, and we need pastures that can also cope. And as I say, in a lot of areas, we're going to be talking C4 grasses, not C3. So, what do farmers need to do and think about? Kelly's touched on this. They need to know the GHG number and benchmark this. A lot of them, or in the dairy industry, the dairy companies doing this for them, which is good stuff. The interesting there is most farmers have no idea what the number means. It's incredibly difficult to benchmark it, given that we've got such a range of tools and they give different figures. Notwithstanding that, they really need to think and plan through what options they have in terms of mitigation and/or offsetting greenhouse gases. And that's quite an exercise, if you like, because in terms of the third point of what I'm saying to farmers at the moment is you need to do a lot of thinking and planning, but don't actually do much because we don't actually know what the rules are. And that we're really waiting on HIWAKA to understand what the farm price is, what the sequestration rules are, what the on-farm accounting system is going to look like. So at this immediate point in time, we don't actually know what the rules are. So as I say, we need to wait, but potentially once we do know the rules, we need to act reasonably fast. And that's me.